Heat.
Uh,
What is heat?
so the first question,
Is
let me
heat.
just back. I don't know why the document goes. So one, define the terms. Okay, so
Heat.
you'll just be giving me the terms and yes.
Heat is. I know only the definition of temperature. How cold or hot a body is.
So the first term is heat.
Heat. Heat.
Okay, so what is heat? That
Not
means
only for
that
them.
girl also had the same problem. She never knew the difference between temperature and heat.
Temperature is how cold
She thought it
or
was
hot
the
a
same
body
thing.
is.
Okay, if you say how hot or cold a body is, that is a bit of that's not a mature definition. That's not how a physicist would define temperature. That is a layman way of saying it. As a physicist, you will say temperature is the measure, or it is a measure of the average kinetic energy of the molecules in substance. In other words, the faster the particles that make up a substance are moving, the higher the
The
kinetic
higher the
energy.
temp, yes, the higher the
The higher the
temperature.
temperature, exactly. Now, and also temperature is measured in Kelvin. These little
Mm-hmm.
things, students have a
But
lot of
heat,
difficulties with it.
heat is heat does have the same definition as temperature.
No, heat, temperature is measured in Kelvin. Heat is a form of energy. Temperature is not an energy. Heat is a form of energy. Heat is the energy that flows between 2 points,
Is the
A and
definition.
B. Yes, that's the definition for heat. The energy that flows between 2 points that are at a different temperature, or the energy that flows across a temperature gradient.
Write it well.
That is heat. Oh, okay, let me write it. Heat, energy flowing across a temperature gradient.
Temperature.
It simply
Or
means
across
2 points.
across
Voila.
two bodies that have different temperature.
Yeah, two bodies that are at different temperatures. So that's the difference. And now heat is measured in joule.
Joule,
So
yes, I know.
now you are seeing already the big difference.
Mm-hmm,
Temperature
mm-hmm.
Kelvin or degree centigrade, the heat energy in joule. So the second term, I think, okay for that one.
The second term is oh, thermal contact.
Thermal contact. So generally, just like two objects can be physically touching each other, thermal contact will simply be a situation whereby two bodies uh, can two bodies are able to exchange energy. In other words,
Thermal contact.
If you take a body A, for example, at maybe 10 degrees centigrade, and another body B at maybe 20 degrees centigrade, then we say these two bodies are in thermal contact if they can freely exchange each other energy, if they can
Yes.
freely exchange energy among themselves. Energy. Now, a situation in which these two bodies will not be in thermal contact is if you place an insulator, for example, between the two. If you place an
Mm-hmm.
insulator between the two, they cannot exchange energy, so they are not in thermal contact. They are in physical contact, but not thermal contact. So there's a
Thermal
difference.
contact.
Exactly. So Romans 3, the next
In
term.
that thermal contact
Yes.
is a situation where two bodies can exchange freely energy.
Yeah, among each other. Exactly. Voilà. Tell me what is thermal equilibrium? At least it's something that you know.
It's a situation where the two bodies there's no more transfer of energy between two bodies.
No transfer of energy. Are you sure? So you're saying that if a body is, for example, a ball, it's
Mm-hmm.
in thermal equilibrium with another ball B.
There's no
So
more
you
transfer
as
of energy now
are you sure?
because
This
they
is a
have
trap. It's a trap. The point is that two bodies are in thermal equilibrium. First condition, they have the same temperature.
temperature.
They are at the same temperature. Being
Yes.
at the same temperature does not mean this does not imply that they don't exchange energy. This does not imply no energy exchange. On the other hand, it instead means that if they have the same temperature, the rate at which A transfers energy to B is the
Ah,
same as
the
the
same
rate
rate
at
as
which
if
B.
B transmit the
So
energy
the
to A.
second implication, rate of energy exchange.
Mm-hmm.
Rate of energy exchange is the same. That's what it means.
In the thermal
So be very
equilibrium,
careful.
it's a
Yeah.
situation where two bodies at the same temperature
They
have the
have the
same
same
rate.
temperature. That's the first
Wait,
point.
I finish.
Mhm.
Thermal equilibrium is a situation where two bodies at the same temperature have have the same rate. No, exchange. No,
Yeah, they exchange energy at the same rate. Exactly.
right. They exchange energy at the same rate and
Yeah.
exchange energy at the same rate. Mm-hmm.
Mhm. That's it. Was that the last definition? There's something else.
Mm. Yes, what the last. Now
Okay.
number two. What do you understand by
So
the
what do you understand this will mean?
usual behavior of water?
What do you understand by the unusual behavior of water? Give concrete
Yes,
example to substantiate your answer.
unusual
This is a very
behavior of
good
water.
question. I think in
Uh,
ordinary level, maybe if you remember, you used to, in fact, I think this is a
water have an
constant.
unusual behavior.
Yes, water has an abnormal behavior.
Which type?
Okay, I will tell you. So the abnormal behavior of water. So the point here is that, so you tell me, if you take a liquid, right? If you
Yes,
take a liquid, when you hit a liquid, what happens? What happens to the
become
volume
wait,
if you hit? How does the
the volume
volume?
don't change.
If you hit a liquid, if you hit water in a pot, what will happen to the volume?
The volume of water
Yeah,
it become gas now.
it becomes gas, which means the volume increases, the gas expands. So when you hit a liquid, the volume
Ah, the
increases.
volume increase. Yes, yes.
That's that's normal. I mean, all
Mm-hmm.
liquids have this
Because it expand.
exactly.
True,
Now,
true, true.
the so this is what happens, and it is the case for all liquids. No matter if you take a liquid from its freezing point, you heat it up to the boiling point, it
The volume will
expands.
increase.
Yeah. Now, for water, in the case
It's
of
different.
water, it is different.
It's
This is how
square.
water behaves. For water, um,
The same volume
okay,
from freezing to
and here,
melting.
okay, before we continue, if the volume increases, it means that the density
Increase. Decrease.
decreases exactly. Density decreases.
Because it's mass over the volume.
The density decreases. So this is for a normal liquid. Now,
Yes.
in the case of water, when you take water at 0 degrees and you heat it, and you heat it, sorry. So when you take water at 0 degrees and you heat it
To melt it.
up to 4 degrees, so what happens is that instead of the volume increasing, for water, it decreases. The volume of water decreases.
Okay.
In other words, its density increases
Increase.
between 0 and 4 degrees. Now, after
Mm-hmm.
4 degrees, water starts behaving now normally, gets back to the normal behavior. This is what we call abnormal behavior of water.
Wait, when you say it become normal behavior, mean that From now, if volume started
Yeah,
decrease.
yeah. From now, the volume start increasing normally when you hit as from 4 and going
Mm,
upwards. And now the density starts decreasing.
mm.
But between 0 and 4 degrees, when you hit,
Why?
the density increase. That's the behavior of water. Now let us look at the application. And here you may say that God is really powerful.
What are
So
they asking me in the question? You will
they
answer.
ask you to explain the abnormal behavior of your water. You just explain this. The fact that the volume of water decreases when you hit it from 0 degrees, its freezing point, up to 4 degrees, or that its
Mm-hmm.
density increases. That's abnormal
Mm-hmm.
because a classical liquid will not behave like this.
Mm-hmm.
Voila. So that's the abnormal behavior. Now the application. It happens that in the polar regions, it happens in the polar regions where there is a lot of cold. This behavior saves the fish in the water.
Says.
Fish. This is because, okay, look, when we are at 4 degrees,
Mm-hmm.
you know that at 0 degrees, ice has a temperature of 0 degrees. Let us start from there.
Yes, yes.
Voilà. So when the water starts heating, when the ice melts, it's going to melt and up to the temperature of 4 degrees, the water instead becomes denser than the ice. So when the water melts, it goes below the ice
Mm-hmm.
and the ice stays on top. Are you seeing?
Mm-hmm. Mm-hmm.
So the water melts, it goes below the ice and the ice stays on top. Now,
Mm-hmm.
this is advantageous for the fish because the fish is going to stay inside the water, which is at a temperature of 4 degrees,
Mm-hmm.
compared to if, imagine, for example, that water was behaving normally. It means the water will never stay.
Ice.
It means ice will be more than the water and the ice will go below.
Yes, yes, yes.
And in that case, the fish may be feeling too cold.
Mm.
So this particularly saves the fish, actually. And fish is important. It's an important organism, an important piece in the ecosystem. If fish disappear today, then it's the whole ecosystem. I think humanity life will really disappear because fish
I
are
said
really essential.
I don't even eat fishings. I should eat it first.
Voila, exactly. So that's a bit the point, the abnormal behavior of water. It is really useful. And now, why is water? And you know that water makes up 2/3 the of the
Yes.
Earth's crust. It is water.
Yes.
So you can imagine that if this was not the case, then I mean, we'll never eat fish. That's why I said there's a bit of God in this. God is present. So somewhere, somehow,
And you don't know what molecule is doing that of
yeah,
water.
you
You
don't
don't
you
know
know
healing.
that there's God. That's how scientists can conclude.
God is present.
Yeah, God is
I
present.
spoke.
Full stop. So if you are teaching a student and the student asks you why there is God, full stop. God is God. Okay. So the next point.
It's
Mm,
the only application that I can show.
yeah, it is essentially this is the commonest application, like the usual application, the most substantial even. There are other ones that I don't remember, but this is the main one, the main application, or the main use.
Okay.
So now they say, three, it is observed that 55 milliliters of water at 20 degrees completely fills a container to the brim. Okay, so let us
Mm.
start collecting our data. So we are on question 3. So we
Also
have a
that
volume of water of 55
55.5
milliliters,
milliliter of
point
water.
5. Yes, just read
Yes.
the question.
At 20 degree complete
So we're going to say initial temperature 20 degrees. Yes.
completely fill a container
Mm-hmm.
to be brim.
To the brim,
Then
yes, which means it is filled right to the top.
mhm,
Mhm.
when the container and the water in is are heat to 60 centimeter, 60 degrees Celsius,
Okay,
zero
they are
point
heated.
thirty five.
Okay, wait. They reach temperature of 60 degrees centigrade. Yes.
Yes, 0.35 gram
Grams
of
of water
water
is
is lost.
lost.
This is a calculation. I
So it
forgot the
means,
formula. A
uh,
specific capacity now.
yes. So water lost.
What is the
So
coefficient of
mass
volume
of the water that is lost,
expansion? Yes,
which is 0. Point,
35.
mhm.
What is
What is
the
the coefficient
coefficient of
of volume
volume?
expansion
Mm-hmm.
of the container? Mm, coefficient with of the container or of the water. It is the water that expands, not the container.
The
Is there
coefficient of
not?
volume.
It is the water that expands, I think.
If you water, you put water.
So I'm surprised they say, I think here you should have in of the water.
The water thing. Because I don't think that the container expand. Because that
Exactly.
don't change.
Okay. So what we can calculate, we know already that the quantity of energy, I don't know if this will be useful, but we know that the quantity of energy, your quantity of heat gained by the water is mc delta theta.
Yes.
We know delta theta, we know
This specific
c,
capacity.
we know delta
Specific
theta, we know
capacity.
c, yeah, specific capacity of water, we know. The
You
mass
know the
of
mass.
water, okay, we can use the mass of the water.
Laws.
Mm, wait, we know the volume of water that was in the container.
Yes.
So we can try to estimate the mass of water that was present in that container. Since we know the density, we know that density
But you don't know the
is
mass of the
mass on
container.
volume. But we are dealing with water, not the container.
Ah, okay, okay.
If we know the density, we know the density of water. If we know the volume, we can calculate the mass of OV. So here we can
You don't
calculate
know
the
the density of
quantity.
water. They didn't
Yeah.
get the density of water.
No, we know it's a constant. Water has a density of 1 gram per centimeter cube or
Mm.
1,000 kilograms per meter cube.
Kilogram per meter cube.
That's the density of water. So it means
Um,
that an
millimeter is what? Is meter cube.
what milliliters
Is
milliliters is
meter cube.
equivalent to centimeters cube, not meter cube.
In
Centimeter cube.
centimeter cube. Mean
So
that is
to yeah,
liter that's equal to meter cube.
voilà. Liter. No, 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 no. Even liters is still not. Is it meter cube? No, because look, if you want to convert from here to liters, you have to from milliliters to liters, you have to multiply times 10 to the negative 3. That's it now.
Mm-hmm. To the positive 3. Multiply by 1000 now. Put into
We are
liter.
going up. We are going up. Liter is greater than milliliters.
Yes. You multiply.
By 10 to the it's like between millimeters and meters. Which one is greater?
It's
It's
meter.
meters. Which means if you
Yes.
have 10 millimeters and you want to convert to meters, you need
You
to divide by
multiply.
1,000
Ah, yes, yes, yes. Divide, divide.
because yeah, because meter is bigger.
Yeah, it's
So
okay, it's okay, it's okay, it's okay. Yes, divide, divide.
yeah. But even up then, liters is still smaller than meter cube. They are not the same.
Mm-hmm, it's true.
Liters smaller than meter cube. But here, knowing that, knowing that, you can get the mass as okay 1,000 kilograms per meter cube, and you have 1 liter. Mm, okay, we know that milliliters is analogous to centimeters cube,
Mm-hmm.
which means which means that if you want to go to meter cube, it means another 1 centimeter, 100 centimeters is equals to 1 meters. So 10 to the power 6 centimeter cube is equals to 1 meter cube. You see now? So to live from centimeter cube to meter cube, we need to divide by 10 to the negative 6. In other words, this volume of milliliters, in other words, this is what I'm saying. 55.5 milliliters is the same as 55.5 centimeters cube. Now, if you want to convert this centimeter cube to meters cube, we need to multiply times 10 to the negative 6, which means that the density here will be the volume will be 10 to the negative 6 times 55.5 times now the density, which is 1,000 kilogram per meter cube. When you do this, you have 55.5 times 10 raised to the negative 3 kilograms.
Why do you not calculate the density using centimeter cube?
I prefer, well, you come back to the same answer.
No.
I just prefer.
No. If you 55.5 times 1.
Are you sure? Let me check my calc. Yeah, if you put density here. But the problem is that this is gram. You still have to convert to kilogram.
When you divide, it's okay.
So it comes back to the
negative 3. Yes,
exactly. So this is the mass of the this is the mass of the water in the container.
In the container.
So we can say the quantity of heat gained by the water will be this mass, 55.5 times 10 raised to the negative 3, times the specific capacity of water, 4,200 joule per kilogram per Kelvin, times the temperature change, 40. So we can get the quantity of heat gained by the water. Can you calculate this if you have a calculator?
You know the specific capacity of water?
Yes, it's 4,200. It's a constant. Sorry.
4,000.
Let me note it here. 4,200 joule per kilogram per Kelvin.
Expect one day you give us in class as constant.
Normally, he's supposed to give him. Normally, it's not like you have to surprise. So, in these are physical constants. So normally they have to be given.
I should calculate what?
Calculate. Just punch this. Let us look at the quantity of heat gained by the water. After that, we'll check on Google to see the formula for the coefficient of thermal expansion.
$9,224.
Joule. Okay. So this is the quantity of heat gained by the water. But they asked us for the coefficient. I've forgotten the formula to calculate coefficient of volume expansion of the container. So it's but normal because if a certain mass of water is lost, it means by heating, it expands.
The number of kilogram, the number of gram of water, you subtract it from the gram lost, you find the new volume.
So gamma is equals to delta V over the original volume times the change in temperature. What is lost? This is the difference.
Yes, it's true. The volume difference.
So to calculate the volume
corresponding to centimeter cube now. The same thing in centimeter cube.
Yes, I think normally because this mass is in grams. So if I want to convert this mass, I have to use this formula. Yes, for density. So the volume will be mass over density. Yeah, it will be the same thing in centimeter cube. So it will be 0.35 centimeters cube divided by the initial volume.
The initial volume in centimeter is 55.5
centimeter cube. The difference in temperature, 40. Okay, yeah,
40.
which is straightforward. So this gives us, okay, so punch this one. Already the unit will cancel. We're going to have something in per Kelvin or in per degrees if you like.
It's 1.7, 1.58
Per
exponential
Kelvin.
negative 4.
Okay. Wait, I thought.
Mm-hmm. Degree Celsius now. It was in degree Celsius.
It doesn't matter. It's a difference in temperature. You can put your
Okay.
difference either in Kelvin or in degrees. It doesn't change. It's a difference.
Okay.
Okay, it means actually that, yeah, we made use of all the data. But in case the input asks to calculate the energy change, I think this one can be useful. It still
And then
helps.
we're not even supposed to calculate
Yeah,
it.
we're not really supposed to do it. Let me circle the part.
Yes.
Let me change color. Okay, how do we even change color? Okay, so I'm going to say that this part, so this part here is not needed. This part here, just circle that so that we should not make any motion. So at least if you want to revise with it, it can be useful. What interests us here is, so what interests us this. Okay, so is it okay?
Yes.
To the next question, I think that was yeah.
Question 4. Prove that the
Question 4,
relationship between the
provide a
different
relationship, the different
provide the
coefficients.
relationship between the coefficient y or is lambda.
Gamma, I think it's gamma.
It's gamma.
Coefficients
Are you
of,
sure?
I think,
Gamma expansion.
coefficient of linear
Yes.
expansion, surface expansion, and volume expansion. Wow.
Linear expansion, surface expansion,
So
and volume
coefficients of
expansion.
expansion.
Okay.
So we are going to start with coefficient of linear expansion. But let us go back. What we calculated was which coefficients actually? Was volume
Volume.
expansion, volume,
Yes.
right?
Yes.
So if one coefficient of surface expansion will simply replace by the surface, I think, right?
Means
You
that
simply replace V
all of
by
them have the
surface.
same formula.
Just that in one case it will be volume, in the other case it will be surface, and in the last one it will be length. Coefficient of linear expansion will only put the length. I think logically that's what it should be. You know already. The coefficient of linear expansion is alpha equals delta L. The change in the length all over the original length, the rise in temperature. Now, the coefficient of surface expansion,
Plus what?
coefficient of,
It's not finished.
it's all now. This for
It's
linear expansion.
1/L times change in temperature.
Yes.
Right?
Look at the one that we,
It's also very
uh,
well.
L delta T,
Voilà.
surface expansion beta, delta S, ou delta surface area, over S delta T, and then volume expansion, gamma, close to delta V. In fact, it's what we wrote before, over V delta T. That's it. At least this was a Kado questionnaire for someone that read what his notes. This was Kado.
It's almost the same thing.
Excuse me, let me take a cup of water. don't mind actually. Tired of this. So that's it for question 4.
Question 5.
Understand why it's so cool here.
It's true.
Kind of cool. It's winter period. So question 5. Wait, so this first question was how many marks? Let me just see a bit. 15 marks. Wow. So a student that was serious had to read all his marks.
You're not finished. You have to
I
get
know.
question 5.
So an iron rod heated from 30 to 80. The final length of the rod is 115 and the coefficient of linear expansion is with, so you will just be giving me the data. So initial temperature 30, final temperature
80.
80. Yes,
The final length of the ion
115.
is, and the coefficient of the length of
Coefficient of linear expansion alpha. Yes, how many?
is that. What is the
Wait,
original
is
length?
okay, 3 times 10 raised to the negative 3 per Kelvin or per degree.
The degree Celsius. What is the original length and the change in length of the ion?
So what's the original length and the change in length? So we
Yes.
recall. So we recall that alpha was defined as the change in length over the original length times delta t. So if you are looking for the original length, wait, do we know the difference in length? That's the first thing.
No, we don't know.
Okay, but we know that the difference in length is the final length minus the initial length.
Yes, they didn't give us a.
All about the initial length times delta t. So we can easily look for Li. They're asking for the initial length, right?
Yes.
So we can look for Li. We just cross multiply. We have alpha Li delta t plus Lf minus Li. So Li into alpha delta t plus 1 plus to Lf. Please follow with me. If there's a mistake, just let me know. So Li equal to Lf on 1 plus alpha delta t. Okay. So
Wait a bit.
we can
Where's your equal sign?
here is it?
Up, up, up. Is here.
So we can plug in the values
It's
and
okay.
do a numerical application. We have Lf is 115, 1 plus alpha 3.10 negative times delta t, which is 50 degrees centigrade. So just punch this and we should get our answer in centimeters.
I will take it to calculate.
Okay.
Okay. 1 plus. One that.
Okay, 100 centimeters exactly.
Yes.
Good. At least when you have whole numbers, you feel comfortable that you can be having the right answer. Okay, there's the next part.
The change in
Okay, what
length.
is the change in length?
15.
Well, change in length. This is
It's easy
the
when you have already
delta
find.
15. The original, well, I mean, this was Roman 1. Okay.
When you have already find Roman 1, it's easy to
Yes,
find
you
Roman
can
2.
easily find Roman 2. Exactly. Okay, so that was all. You see that the question was not difficult.
Was
So,
very good.
question 2. But this paper, okay, this is the last question of this paper now.
Yes, I don't have question 3. I don't know what question. There's nothing question 3.
Ah, so there was a question 3.
You see question 3, 15 mark, but there's not enough send the picture of question 3.
Okay. And are you sure that this question 2 is even complete? Mhm.
Eh?
Are you sure that this question 2 is complete? Because the question looks short.
I think that is complete.
So they say a container holds a mixture of three non-reacting gases, N1 moles of the first gas with molar specific heat at constant volume C1, and so on. Find the molar specific heat at constant volume of the mixture in terms of the molar specific heats and quantities of the three separate gases.
Basically, gas.
Okay, here you have to do
Mais tellement
some calculations. So a
on a
container holds
nothing.
a mixture of three non-reacting gases. So it means we have a container
Yes.
like this. And inside this container, we have three gases that don't react with each other. So let me just put them like this. So we have N1 moles of gas 1, N2 moles of gas 2, and N3 moles of gas 3.
Okay.
So the gases don't react with each other. So they exist like separate entities in the mixture. Okay, so the first gas has molar specific, or the specific capacity is C1. So here, C1. The second gas, C2. Third gas, C3. It looks like we'll have to apply the gas laws. So find the molar specific heat at constant volume of the mixture in terms of the molar specific heat. Okay, I understand what they're saying. Understand. So what they want is that you should find C, the specific capacity.
For which gas?
You should find C for the mixture, given this data.
For
That's what
which?
they're asking.
But say that the gas cannot mix now.
Yeah, the gas cannot mix, but the three gases can behave as one gas, even if then because it's a mixture, even if they don't react with each other. The overall system has a certain specific capacity. It's just like when you have resistors now. When you have two resistors in maybe parallel, the two can behave as if they were one,
Mm-hmm.
even if they cannot. Voila. So it's a bit the same thing. So we need to compute this. Bon, which formula can we use that relates number of mole and specific heat? The heat capacity divided by the number of mole. Okay. So what do we do? If you remember in Hausa, we used to say that the total pressure exerted by a system in a mixture is equal to the pressure of a pure component times its mole fraction. It is equivalent to this
Yeah, to the
because
external
here
pressure.
the, the total specific heat of the system is equal to the mole fraction of each component. The mole fraction of each component means it's mole all over the sum of all the number of mole times its own specific heat, C1. So you do this for each of the component
Mm-hmm.
and C2. It's exactly like Raoult's law and C3. So this implies that
But if we see that you're calculating C1, no, C for
here is C of the mixture. C of
okay,
the
okay.
mixture. C of the mixture is the mole fraction of the first gas
Yes.
times C of the first gas plus the mole fraction of the second gas times C of the second gas plus the mole fraction of the third gas times C of the third gas. The mole fraction simply means the number of mole of that gas divided by the total number of mole.
The total more.
So we can just write that the C of the mixture is given by N1 C1 plus N2 C2 plus N3 C3. All this divided by N1 plus N2 plus N3.
Mm-hmm.
This was what you have to do for 10 marks. Of course, he gave many marks because he knew that many people will not read your notes, so they will not have it. But actually, there's nothing difficult.
The mark is too much.
So that's the thing. But the reasoning is worth it. But even the first question that we did, 15 marks, there was nothing exceptional. But it's true that there was a bit of calculation, but there was no big deal. That's the answer. You can ask him. That's the answer. So if you find exercise 3, we can check that maybe on Saturday.
Mm-hmm.
We'll check that on Saturday or on Sunday.
Mm-hmm.
Yeah, prepare also the chemistry questions. Yeah, I'm tired. I'm up since morning.
math question.
You said your teacher, you have never done a chemistry class.
I say physics class, not the chemistry class.
Okay. Okay, then if it's math, prepare math. In fact, prepare the ones that are urgent because we may only have again Saturday, Sunday, and maybe
Okay.
Monday if possible. It's not sure, but
I'll prepare.
okay. Then go and rest.
Thank you.
So
Even